Right, so final lesson of Java 4 and also for the whole Java course, basically. And I would say, again, that this is probably one of the hardest ones. Maybe it, like the hardest, at least in my opinion, it is. But anyways, okay, so Java 4 lesson 8, and we're talking about sorting methods. So I kind of alluded to it last time when we talked about recursion. I was like, oh, there's a way to make an array sorted. Yeah, this is what I'm talking about. So yeah, we're just gonna go through some different methods of it and look at some code, look at some explanations, look at some badly drawn diagrams made by me. But yeah, moving on.
That sounds like
Yeah, it is. Okay. So inefficient sorts. So we're gonna split into two categories. One of them is the inefficient sort. So basically, by inefficient, I just mean like it's gonna take a while. If you have like loads of code, it's better not to use these because they're gonna take a while and they're not exactly the most efficient. Like there's more efficient ways of solving this problem. And there's efficient sorts then, which are pretty time efficient and are suggested for certain circumstances. Okay, moving on. So sometimes you would want to sort an array, list, or other collection. For example, like when you're doing binary searching, you're going to want to sort the array or list or whatever. So we're going to have to go through how to do that. So starting with the inefficient sorting methods. Okay, so the first inefficient sort we're going through, there's 3 in total. The first one is called a bubble sort. So what this does is it takes the original array, switches 2 values at a time until the largest is at the end of the array. Then it takes the array again, minus the largest value that was just sorted, and does the same thing to that little subarray. And then it continues doing this until the array is sorted. So it's hard to imagine it right now. There's diagrams and also code for this. So you'll see. Yeah. This was probably, I would say, maybe the most inefficient of the inefficient sorts. Oh, wow. Okay. There's nothing else I had to say for this one. Yeah. So drawing. Oh, I can't. Okay. Sorry. My cursor is not operating today. So drawing of how bubble sort works. So if we had an integer array of 3, 1, 4, 0, -2, then pretend this is like how it would go through each step, okay? And ignore this part at the bottom. So first it looks at this number 3 and this number 1. So it's gonna say, oh, which one's larger, right? It's 3, right? So it's not in the correct position because 3 is on the bottom. And so it swaps those two. So it becomes 1 and 3 now. And then the rest is still the same. So next it compares, sorry. Okay, so next it compares 0 and 4. Actually, no, I'm good. Okay, sorry. So it compares 3 and 4 next. And then because it's in the correct position, 3 and 4 are relatively nice. And so it stays the same. But then it moves on to 4 and 0. So it can see that, oh, 4 is larger than 0. So and it's still in the bottom. So we have to switch that. So it becomes 1, 3, 0, 4, -2. So that's good. But then we move on to this one, this pair right here. So 4 is larger than -2, and yet it's still in the bottom. So we have to swap it again. So it becomes 1, 3, 0, -2, 4. So in that case, you can see that 4 is already the biggest number of that array, and it's at the bottom. It's like at the top, right? So we don't need to consider that anymore because it's already sorted. And doing so would just take more time and it's unnecessary. So we just ignore that for now. So I put this line here to signify that we're not looking at it anymore. So in that case, we're only looking at 1, 3, 0, -2. So we do it again. So we look at 1 and 3. That's still in the correct position. Nothing needed there. Then we look at 3 and 0. And again, 3 is bigger, so we still have to switch it. So it becomes 1, 0, 3, -2, with 4 being like ignored right there. So, and then we'd have to look at 3 and -2. And so again, because 3 is bigger than -2, we have to swap it. And it becomes 0, sorry, 1, 0, -2, 3, 4. And in this case, again, 3 is already big. It's already like at the top. So we just ignore 3 and 4 because they're already sorted. So moving back up here to where I continued. So then you have to look at 1, 0, -2. 1 and 0 are not in the correct position, so we swap that. 0, 1, -2, with 3 and 4 being ignored. Then we have to look at all of this. So 1 and -2, it's not in the correct position. 1 and -2, so we swap that. So it becomes 0, -2, 1, 3, 4. And then 1 again is being ignored because it's already sorted. And lastly, we just swap these two because they're not in the correct order. And then you'd see it becomes sorted array. So -2, 0, 1, 3, 4. So you can kind of see how this is like kind of inefficient because like you have to go through each one and swap it with a neighboring answer. And then like when like you could probably already just pick up and move it there. So it's kind of inefficient in that way because you continually have to swap it again and again with its neighbor. So in a way, it's kind of most inefficient, if you get what I mean, but you'll see. But yeah, that's it for that bubble sort diagram. That's more of an example of how it would work. It's not necessarily how it exactly would work, but you can kind of get the idea of how it would work. Okay. So this is how you would do it manually, by the way. I think the code is next, or maybe an explanation. Okay, code. So the code was too long, so I had to split it onto like 2 different pages. Another reason why there's like so many slides, but okay, so usually the code, okay, I'm not talking very well today. So there's an array, and I did it for testing purposes. You don't, again, like this can be whatever. So we call the bubble sort, and the bubble sort code is like on the next page, I believe. And then here you can see that I'm just like going through the array to print it out. For testing purposes, again, you don't have to have this. Okay, I'm pretty sure you guys all understand that top part. This is the important part. So what this is, you can see it takes in an integer array, and be warned that bubble sort doesn't have to be exactly for integers, like any of the sorts. It doesn't have to be exactly for integers. It can be anything, and that includes like doubles, strings. It'd just be like a different implementation then. So, okay, this might be really confusing once you do this, and like it's important to understand each part of it. So, first you initialize a pass integer variable, and you set it equal to 1. So, what this is kind of saying is this pass variable is mainly for to document how many elements you have already sorted into the correct position. So this is where you see like how I kept ignoring the ones that are already sorted at the end. This is what it's for. And then you have a Boolean exchanges equals false. And that kind of just basically tells Java whether or not there's still more to go through. And then you can see like at the bottom here where it says while, that it's basically using it as a condition. So I know I haven't like actually gone through this, but probably will someday as like new material in the for loop section. But yeah, so you guys haven't specifically seen this, and it's the do while loop. I'm pretty sure you've heard about it before. So the basis of a do while loop is basically so that it goes through the loop at least one time, and then it tests the condition, and then it runs over. So it's basically a while loop, except that it like has to run at least one time. That's the basis for that, and hopefully you understand what that is. But going into this, you can see that first we're setting exchanges to false, and that's like, again, to test whether or not there is more to go through, and you can see like over here it has exchange is equals true, so it's definitely going to become true at some point, depending on where it goes. But yeah, that's the point of the exchanges. And you can see that you can sort of kind of see here where it starts ignoring the ones that are already sorted. Because, so kind of think about it. So when you're saying array.length minus pass, you're basically saying that cut off whatever that is already sorted. We're only going to go through a certain amount so that we can do it. And that's kind of signified here by this. So when you're minusing pass, you're basically saying ignore the sorted ones. When you go up here, and sorry about the formatting, it's really bad, but you know, I copied and pasted it directly from somewhere. It's my code, don't worry, but like, you know, it's not exactly, formatting's not very great. Okay, so this one, again, kind of looks really confusing. So does this part. But the point of it is so that it's saying that if the current element is greater than the next element, so that's kind of like where it says if the current element is greater than the next one, that means like there is like incorrect placing. That's basically what it's testing. Then you do all this stuff. And at first, you're probably going to look at it and be like, what the heck is this saying? I remember I probably tested you guys on this before. So like, well, I at least gave you a problem on this, but this is how you swap elements in an array. And once you look at this, you probably could start to understand. So you're basically saying, we're creating a temp variable to contain the current element so that it doesn't get lost. We're setting the current element to the next one, which we said was smaller than the current one. And then we're saying the smaller one, the original smaller one, equals the temp. So, and if you remember, look, it's the current element, basically. So in that way, you can kind of see that it's swapping the different elements. And this is how like you get that swapping between the pairs. This is where it's happening. So basically, if you're going to turn this into English, it's if the current element is greater than the next element, then swap. So that kind of like simplifies this exact like entire code. And then exchange is equals true. So how this works, you can think about it is, so for example, if this pass variable, it was already, it turned, when this evaluated, it turned it into, for example, 0. It was exactly the length of the array.length. Then wouldn't this for loop not execute? And if you look at this in total, and I know it's broken up into 2 parts, but try to imagine it, then that would mean that if this for loop doesn't execute, it would never be able to get to this exchange equals true. That would mean that it would go immediately after the for loop to this pass, and then it would evaluate to false because it automatically sets exchanges equals false here. And if it doesn't get to this and it just increments pass, then it's never going to become true. And then the loop ends and your sort is finished. So that's the purpose of an exchange variable. Sorry, give me a second. Sorry, never mind. Yeah, so that's the point of an exchange variable. And then you have to increment pass at some point, you know, because otherwise you're never going to get to that for loop end. That's the point of the pass incrementing. And then you have the while Boolean part that just keeps track of like whether or not the loop should end. But yeah, hopefully that kind of like made more sense after like I went through each part of it. The point of having this kind of large code to simplify is so that you're able to memorize it and be able to do it. Actually, not memorize it, but it's for you to understand it so that you don't have to memorize it later, and that could cause potential confusion. All right, and that's for that code. Also, another note, be aware that you don't have to have exactly this. Again, there's different variations you could do. So for example, you don't have to do this exchange variable. You could cut it out and do some different structure. There's different variations and you can do what you see fit. Okay, sorry, I really need it. Okay, yeah, but that's the code for that. Bubble sort, be aware that there's different variations and that I'm probably not going to test you on, most likely not going to test you on actually reproducing this code, just because like I think that's kind of overrated. Well, not really overrated, but it's a bit hard to do like directly at once. So I might ask you to try, but I'm most likely not going to ask you to do that. There's a chance I might ask you on the test, but just be aware, just understand how this code works, and I think that should be good. All right, moving on to the next one. Insertion sort, the second of the inefficient sorts. Right, so kind of like you can tell by the name in a way. So it starts from the beginning of the array and it works its way down the list. If there's a value that is out of place, it takes that value and inserts it where it should be, it's supposed to be, moving every value after that when the value is placed where it's supposed to be, back a place. So in a way, it's kind of more efficient if you think about it. So again, I have a diagram and it is right here. Ignore the weird tilt. I took a picture of this at the wrong angle. So it's a lot simpler and you can see that it's like drawn a lot more simply. There's not a lot of comparisons to be made. Well, not comparisons, but like there's a lot less writing. So again, it's the same array. So again, like it starts from the beginning and then it works. So it says, oh, three should be good. And then it sees 1, oh, it's out of place. So we move it to the front. 1, 3, 4, 0, -2. And in this case, you kind of can't tell, but when it's moved to the front, it pushes everything back a pace. So that's why they're all there. So, okay, we can go and we say 1, 3, 4, they're all good. And then 0 is not in the place. So we move it back to the front. And then again, you're moving it back, everything back a pace. So 0, 1, 3, 4, they're all good. -2, it's not in place. -2, move it to the front. 0, 1, 3, 4, and you're sorted. So again, it's a lot simpler than bubble sort in that way. And it's probably like, you could probably relate to it in a way. Kind of like a claw machine. Like picking the wrong one and then putting it where it should be. Like, might not get this, but like the reason why it's kind of inefficient is because you have to push everything back. And that takes like a decent amount of time. And that's why usually people say that this is inefficient. But otherwise, the algorithm, like when you're solving it, should be pretty nice. It's also just that like, if you're gonna go through like a 100 element array, then it's gonna take a long time to go through all of that. But yeah. Okay, moving on to the code. So I fit it all in one page this time. So pretty much the same array. I don't know. Testing purposes again. Insertion sort. Printing it out. And come to the actual important stuff. Oh, geez. Sorry. So again, we're taking it into an integer array, and remember that you don't have to have an integer array. Like it's gonna change. Like the implementation is gonna change with whatever data type you're doing. So just be aware of that. So kind of similar in this way. So we're going through everything this time, except for the first element because it's already there. And when it's considering the first element, it can't consider anything else because it's already in the correct place, and as Java realizes. So that's why we don't consider the first element when we're doing this like big loop. So we keep track of the value. And so this is basically when, because we have to find the correct place, where the value is supposed to go, then that means that everything's gonna like switch up. So we have to do this value variable so that we're not like completely erasing the value afterwards. So that's that. And we're also just keeping track of the index, the current index, because that's probably also going to change. Yeah. Actually, no, we're using this to like as an incrementation so that we find the correct place. So here we're kind of, this is the whole while loop here is trying to figure out where the correct place is and where to put it. So we're saying that is it as long as index is greater than 0 and that the value, which is this, the current value, is less than array index minus 1. So, okay. Sorry, I wasn't thinking. Yeah, so basically we're just saying that as long as this is not in the correct place, because we want it to be, okay, just like, my brain's not working today. Just think of it, this part as like making sure that it's not in the correct place yet. Oh yeah, okay. Sorry, my brain finally started working. Okay, so when it's saying like value is less than array index minus 1, so that's basically just saying that if the index below it is greater than the value, then that means that it's still in the incorrect place because we want the value to be less than. Actually, no. Yeah, we want it to be like greater than the value directly beneath it. So that's why we have to continue moving it. And so basically you can see like this array index equals array index minus 1. That's just saying that, oh, we're going to move everything to the left. Okay. Sorry, it's late. I don't know. But yeah, this is basically just moving like back a pace or front a pace. And then we're minusing because we're going to go on to the next one below it. And finally, you just see like an array index equals value. That's just saying that, oh, after this loop goes, we finally found the correct placement for the value here. So we just set it to the value, set the index that we found to the value because everything else would have moved back a pace. Okay, hopefully I explained that clearly. My brain kind of like blinked out at a few places, but you know, hopefully you understand what I mean by that. And try not to like think about the specifics. Actually, no, think about the specifics. Just like take into account that like I didn't explain exactly this part and this part very well, but the other parts are good. So basically it's just saying that this goes through the loop. This keeps track of the current value that we're trying to store for. This keeps track of where the correct index is. This part just says, oh, if it's not in the correct place, continue moving it back to try to find the correct index. This sets it to this sets it to the correct index. And again, like note that there could be variances to this code. Alrighty then. Selection sort. So you can kind of like confuse insertion sort and if selection sort, just make sure that you understand the difference. So this picks the smallest or biggest, depending on like how you implement it. It's usually like the smallest because like in the generic code, it's usually the smallest. And I'm only going to ask you to find smallest most likely. So it picks the smallest number and switches it with the first element. And then it finds the next smallest number and swaps that with the second element. And it continues doing that until the array is stored. So it's different from insertion sort in the fact that that it's swapping instead of inserting. And it's different from bubble sort in the way that it's selecting the correct one and then swapping. So it's kind of like a combination of both of them. Try to think of it like that. Drawing. Okay, so same array. So instead, sorry. So you can see here that we go through this array. Oh, it sees that -2 is the smallest, so we swap that. -2 is here, 3 becomes here now. Go through this array. Oh, 0 is the next smallest, so we swap that with 1 here. So because -2, 0, 4, 1, 3. Go through this array. Oh, 1 is the next one, so we swap that with 4. So it becomes -2, 0, 1, 4, 3. And then lastly, there's only the 3 and the 4 left to be swapped. So you swap those two and you're done. So again, sort of kind of efficient in a way, but again, kind of slow and inefficient. These are like having to constantly compare it with the other values. All right. Selection sort code. Okay. So you have the array, call, and testing. That part's not important. Important part is here. So in a way, we're kind of just going through the array again, but because again, that like you have to consider the fact that like a part of it's already like you can't consider all of the array at once, because if they're if the sort's only considering one element, then it's already sorted in a way. So there's no point in doing that extra one. So this min index gives off the name, like you can probably tell what it's supposed to do. Keeps track of the minimum, like the smallest index. And then we're saying that from this index, and then as long as the j is less than array.length, so basically going from whatever the min index is to top, then we're just saying that if this j value is less than the array min index, so basically it's saying that if the current j value in the element is less than the min index, the supposed smallest value. So basically it's saying that, oh, if there's a value smaller than the current minimum value, then we turn this minimum index into j, because that would become the new smallest element. So this array is kind of just trying to find the minimum, the smallest one. And then this looks familiar. What is it? It's the swapping part. So same kind of thing. Temp equals array.i, array I equals array index, and the array min index is equals to temp. So basically, going through the array, find the minimum value, and then swap it. And then because I increases each time, then you're basically cutting out the ones already sorted. So that's how that goes. Okay, so again, this is for an integer array, and also you can have different variances. Okay, so that's that. Efficient sorts. Okay, so now we move on into some of the more efficient sorts. So they are efficient, but they can be hard to code. So like, not going to spend too much time on the code. Probably, I'm going to go through it still, but like, you know, like most definitely probably not going to ask you to code this. I'll just ask you to know the definitions and know how to go through it. Okay, merge sort. So it splits everything into two orders. So it swaps the values if they're not in order, the subarrays, and then it merges them back together. So again, it's efficient. So you have two arrays. One is a current array and one is a final array. You can't override a current array, so you need another array to sort values. Then that overrides the current array. When you are sorting the subarrays and you see indexes that have ++ after them, they can increase by 1 after the assigning of the variable. Okay, you'll see that more with the with the code. You'll get what I mean by the ++. But so basically, it's just saying that you're splitting the current array into two, and you continually split it into two, and then you merge them back together. So while you're merging them, you're basically sorting them. So when you split them all into one, element arrays, then you merge them together. So merge them one by one so that they're all together. You'll see what I mean by the diagram. Speaking of the diagram, okay, same array. So you can see we're splitting into two, and usually like splits around here. So splits into two, splits into two, and then splits finally into one element arrays. And then we're merging it back together. So you can see 3 and 1, they merge. 1, it becomes 1 and 3 because it sorts them while they're merging. Over here, it sorts again, -2 and 0. And then you merge this part back together. So -2, 0, 4. This is still the same. Then finally, you merge it into the final array and you're done. So yeah, this is considered more efficient because you're actually taking advantage of, you're doing recursion in this case. So it becomes more efficient in a way. Okay, code. This is not my code. This is actually from my teacher. So yeah, again, not my code. So over here, we kind of just make an array, test it. So you can see that like it splits this into 2 different arrays, and you don't have to do this. This was kind of just for simplicity's sake, because you can see down here that we need 2 different arrays. Sorry. You kind of because you can see like this second method needs like a lot of parameters, because you can see that this merge sort calls this merge sort. And the reason why they did another method was to simplify what you had to put in. So in this case, it was so that the user only had to input the array instead of this gigantic string of numbers. Yeah. So don't have to do this. This was all optional, but you can see that it passes in an array, a temporary array, and to like put the new values in, it has a low variable and a high variable. Kind of similar to binary search in a way. Okay. This continues on for like 4 slides, by the way, so. Okay, so we have a base case here. And again, like this is using recursion, so that's why we have to have a base case. And the reason why we went over base cases, actually recursion, in last lesson. Okay, so basically it's saying that if low is equal to high, return. We're establishing the middle value. And again, this is similar to binary search. Okay, next we have like 2 different calls. So this one splits the array from low to current mid. So this is where we start splitting into 2. And this one again, we're splitting from mid plus 1 to the high, splitting into 2. This continues doing it until there's only 1 element in each subarray. Because after it's all cut into 1, then it has to re-execute the stuff that's after base case, or like after the method call. So it continues going on to this. So in this way, it's kind of hard to understand sometimes. And so it's basically saying that we set a low index, a left index and a right index. So one of them is low and one of them is mid plus 1. I don't know what, okay. Yeah, I don't know what this means, but like, ignore that part. Probably gonna delete it later. Move on to the next slide. We have another index, and that is low. And so you see like a bunch of different whiles. So we're saying as long as left index, which is low again, that's the like lowest value, is less than or equal to mid, and the right index is less than or equal to high. So right index again is mid plus 1. And then we have some like if statement. So we're saying that if left index is greater than mid, which it kind of shouldn't be. Actually, it could be. Remember, this is like a or, so actually, that's not the correct name, sorry. It's saying that at least one should be true for this to execute. So we're saying if left index is greater than mid, so if left index is not greater than mid, then it moves on to the next condition. Don't have to worry about that, but it's saying that you do something like this. So, okay, to be very honest with you, I don't understand this very well, and it can be very confusing. So you're probably going to have to go look at this later on your own time. But what I wanted to pinpoint directly here are these values. So you can increment it within brackets. That's fine. Like you can use that as an operator. But what I specifically wanted to pinpoint out, if we go on to the next page, never mind, there is none. Okay, sorry. What I wanted to pinpoint was that sometimes instead of putting it after your variable name, you can always put it like right here, like right where my cursor is. You can put it before the variable name. So it makes a different output because when you put it after, you're saying that first use this value for this, So it do array right index, and then it increase. But if you do it before, it increases first, and then it uses the variable. So if you put it before, then you're basically using the right index plus 1. If you're doing it after, you're doing right index, and then you're adding 1. So yeah, I'm not gonna go through this pretty much. I need to like clean it up a bit anyways. So yeah, I'll like write more comments in here about the actual use of it. But for now, just understand that, like, look at how long it is and you'll see. Point is, this is merge sort. You can see how long it is compared to other ones, and it's more efficient, but it's also harder to code. One day I'll truly master how to do this, and again, I'm still learning, and then I'll let you guys know, but probably not going to test you on this anyways. Just know that this exists and how it works. All right, so quick sort. This is another sort, and this is faster than merge sort. It's also more complicated. So a good way, so for quick sort, you need a pivot, and a good way to set a pivot is that the pivot should be close to the median of the array. Okay, wait a second. Yeah, do something. Okay, now that we took a break. So again, like quick sort's faster than merge sort, and like quick, quick sort, but it's more complicated. So again, you need a pivot for this, and like a pivot's kind of crucial to quick sort. Everything depends on that pivot. So I'll explain more about what exactly it is. But like, a good way to set it is that the pivot should be close to the median of the array. One way to ensure that is to take the first, last, and middle element and take the median of those. So basically, whichever's the middle element of those. So when you make a pivot, then you place it in the stored location with a property that every element less than a pivot is before and every element more than a pivot is after. So basically just kind of separating it again, but having the pivot in the middle so that everything that is less than pivot is before it and every element that is more than it is after it. So that kind of sorts into two separate arrays that are kind of already sorted. And then you recursively sort it so that sort those parts so that they're all sorted. And I haven't, okay. Yeah, but that's the basis of it. This is another explanation that's probably more concise. Not concise, actually, it's probably not the concise. But yeah, so another explanation of it. To the pivot, swap it with the first element. So again, kind of similar. If you take the first, middle, and last element to choose a pivot, you compare the three, and whichever one has the value that's in between the other two, that would be the pivot element. Have a pointer named low and a pointer named high. They start from different ends. High starts at the end and low starts at the start. High is the number lower than the pivot. Low is the number higher than the pivot. Okay, it's basically saying that one starts at the very end of the array. The other one starts at the pivot plus one. Because, like, remember, you swap the pivot with the first element so that the pivot's already at the beginning. So yeah, so you continue moving on, and you'll see more with the diagram, but so it's basically keeping an index. So we move it until you find an element that is, so for the one at the end of the array, let's call it high. If high finds an element that is not where it's supposed to be, so if it's less than the pivot, then it stops there. So high is always decrementing down. So when it finds one that is not in the correct place, it stops. For the low variable, the one that is near the pivot at the beginning, it increments. And when it finds an element that is bigger than a pivot, that's not in the correct place, then if they both find an element that's not correct, then they swap those two so that they're in the correct place. So it continues doing that until they're both equal to each other, and then it ends. So yeah, kind of what it says here. If one of them are not correct in the correct place, then you increment. Okay, this explanation is really bad. I need to reword this. So basically, you're just incrementing with low or decrementing with high until you get a number higher than the pivot for the low variable, and then you swap the low and high. The numbers, yeah. So like when you're swapping those two, you're swapping the numbers that are there at the pointers rather than the pointers. Then you move on to the next element in their respective path. If low is equal to high, then you decrement low by 1 and then swap the pivot element with low. So basically, because we already sorted them into their like bigger, less than halves, then we already put the pivot there so that it's in the correct place. And then you just recursively sort the two parts until they're all sorted. So this one's the more explanatory way. I need to like change it later, but you know. Okay. That's the explanation for it. This is the drawing. So same array, it's just that we add like a pointer this time. So originally there was 3, 4, -2, but because we have to take the first, middle, and last element and take the median of those, you can see that 3 is the middle one, so that's the pivot. We move it to the front and we swap it with 4. So it's already there. I didn't add the original one, probably should have, but actually no, it was already in that place anyways. Okay. Yeah, because it was the median element is already in the front, then we don't do anything to it. We have the low index and the high index. So this one is -2 is not, it's lower, it's less than the pivot. So it stops there because that's incorrect placing. So this one, it's low, it's lower than the median, than the pivot. So that's fine because it's supposed to be there. Then it goes to 4, and you can see that it's incorrect because 4 is bigger than pivot and it has to be swapped. So we swap -2 and 4 because they're both in the incorrect placing. Becomes 3, 1, -2, 0, 4. And then you see that, oh, it continues going so that -2 is correct, 0 is correct, but then they become together because there's nothing else and it's in the correct place. So Java keeps track of where the correct place is. So in this case, it moves this pivot element back to where it's supposed to be. So right here, 1, -2, 0, 3, 4. And then it's in half and then towards this side and this side. And then you get this one. I didn't want to write it out again, but like, I think you kind of get the point with it. Basically, when you're doing this again, you're just choosing a pivot again and then swapping in it until it's sorted. But yeah, that's the basis of it. And just keep note that, again, this is probably not exactly how it works, but basically what it works. So as long as you get an idea of that, then it should be good. Last notes, and I believe this last slide. Radix sort. I'm not going to put like diagrams for this one because like kind of self-explanatory and also something you should be familiar with. So this keeps track of the number of times each element occurs, then rewrites the array using the elements and the number of times it appears in it. So similar to a dictionary, think of it as a dictionary. I'm not going to test you on this. I'm going to test you on a definition. That's it. That's it for radix sort. And other notes. So kind of a note on when to use which sort. So for arrays with like 7 elements or less, use insert sort, selection sort, etc. Otherwise, use quick sort or merge sort. So those inefficient sorts, they're only good for small arrays because again, going through big arrays are like really hard for them to do. So if you want to sort something and you want to do it with like small arrays, then sure, use an inefficient sort. That's fine. But if you're going to use like an 1,000 element array, then use quick sort or merge sort, please. Even though they're harder to do, they're more efficient and it would help you save time. But like, again, you can kind of notice, like, I'm just telling you now, the quick sort code is pretty long. But like, I'm just saying that merge sort or quick sort, they're harder to implement. So if you don't need to implement it, don't implement it. But if you do, then implement it because they're worth it. Otherwise, for like small arrays, then use insert and sort inefficient methods. But yeah, I think that's it. It ran on for too long. I'm probably gonna split this into like 2 different lessons later. But yeah, this is it for this lesson.